Hi there, Mr. Sutton here with the AB Calculus 613 homework answers on volume with solids of revolution. For this no calculator question, we want to rotate the region enclosed by the x-axis, the line x equals 3, and the square root function around the x-axis here. So let's find the volume of this thing. So visually, you're not allowed to use a calculator on this one, but you could very quickly draw the square root function. Here's a picture of what we're dealing with. You have your square root, you have this vertical line, and you have this region in here that we want to rotate around the x-axis. So since we are dealing with a region that's flush against the axis of revolution, there's no spaces between our area and our axis, we can use disks for this one. So then circles are going to be our cross-section area. We're just going to go with pi r squared. And in terms of x, how far is my radius from the axis of revolution? Well, the distance between my outer region of my my area here and the axis is just going to be the square root. So I can just write this as pi times square root of x squared, which is just pi times x. So this is my area function that I now have to take the integral of. And what are my limits of integration going to be? Well, we're going from 0 to 3. So pi x dx will be our integrand here. And taking my antiderivative, this is going to be, let's see, pi over 2 times x squared, evaluated from 0 to 3. So we have a 3 plugged in. We have a pi over 2 that I'm going to actually take out, and then I'll plug things in inside here. So we have 3 squared minus 0 squared. So this is pi over 2 times 9, which is 9 pi over 2. And then we also have this 0 here that we don't really care about because you're just multiplying pi over 2 times 0. So 9 over 2 pi then ends up being our answer, choice C. On this problem, R is the region bounded by y equals e to the x, the horizontal line y equals e to the third, and the y-axis, the line x equals 0. So we want to know which expression here gives the volume of the solid when we revolve this region around the line y equals -1. This is a calculator question, so it's a good idea to actually graph all this out and see what we're dealing with. Let's do that now. So I'm going to be graphing three things here. I've got my e to the x function, the line e to the third, because I don't really know where that is. It's whatever 2.7 something times or to the third powers. And then we also have our axis of revolution, the line y equals -1. Let me do a zoom 6 just to see if I have any of this on my screen. So here's e to the x, and I'm not seeing the next thing. That's probably a little off screen. Here's my axis of revolution. So this e to the third line must be a little bit higher up. Let me adjust my window a bit. I'm going to go from, let's see, 0, because that's where things start, to, well, how far out should I go? My limits of integration based on all the answer choices are from 0 to 3. So I'll go out to, let's say, 3.5. I don't want to go too much further out. And then zoom fit this thing and see if I can get everything on the screen at once. So there's my exponential. There's my horizontal line. And down below, there's my axis of revolution. Okay. So I need to, I could set these things equal to each other officially to find the limits of integration if they didn't already give me that in the answer choice. But we clearly see here that e to the x and e to the third are going to have to intersect at 3, right? Because e to the third equals e to the third. So there we go. Limits of integration. Now, we're taking this region in here and revolving it around the line y equals -1. Because my region and my axis of revolution are not flush against each other, because I have this empty space in between, that means I'm going to have to use washers, donuts. So I'm going to have this area formula, pi times big R squared minus little r squared. Basically, big circle minus little circle when we revolve these to get that donut shape. So now I have to figure out my big R and my little r. Now, the nice thing about this problem is I don't actually have to plug anything in the calculator, because I just have to match one of these answer choices. So for big R, that's going to be the outer radius. That's going to be the distance from the outer part of this region, the region that's further away from my axis of revolution. So to get from here to here, I have a distance of e to the third minus -1, which is really e to the third plus 1. So I'm going to write this as pi times e to the third plus 1 squared. And then for my inner radius, I've got this e to the x function minus -1. So this is e to the x plus 1 then, gives us this inner distance. And we're squaring that. And now just putting that in the integral, I have the integral from 0 to 3, and I'm going to put this pi outside here. You're allowed to do that because it's just a constant. And inside now we have the rest of this stuff, just basically cut and pasted in here. And now we just have to carefully match one of the answer choices. So the only answer choice that has all this stuff in it is choice E right here. So that's the one we're going with. For this problem, we want to find the volume when we rotate the region between secant of x, the y-axis, the x-axis, and this other vertical line around the x-axis. So just trying to visualize this, and you have to because this is a no calculator question. We have our secant function, which in parts kind of looks like a smiley face that's elevated above the x-axis. And we also have the x-axis itself as kind of the bottom of this function. So since the x-axis is one of the bounding areas and you're rotating around the x-axis, visually there's no space between your area and your axis of revolution. So for this one, we're going to go ahead with discs rather than washers. Our cross sections are going to be circles, and we can use pi r squared as kind of our area of our cross sections here. So the radius is just going to be the distance from your axis of revolution, the x-axis, to the top of your function. That's going to be this secant right here. So we can write then pi times secant squared of x for this area function. Now there's no calculator allowed, so you actually have to integrate by hand. We're going to have the integral from 0 to pi over 3 of this stuff, pi times secant squared of x dx. And doing this one by hand, antiderivative of secant squared of x is just tan of x, and we also have a pi that's going along for the ride. So this is what we have to evaluate now from 0 to pi over 3. So to make this a little bit easier on myself, I'm going to yank this pi out of here, and inside of parentheses now, I've got the tan of pi over 3 minus the tan of 0. Well, what is the tan of pi over 3? I don't remember off the top of my head. This is the tan of 60 degrees. So I'm just going to kind of do some scratch work over here. This is really sine of 60 over cosine of 60. Sine of 60 is root 3 over 2. Cosine of 60 is 1/2. Dividing these halves cancel out, so you really just have radical 3. So then this is going to be pi times radical 3 minus, what's the tan of 0? That's the slope at 0 degrees, or 0 radians. So that's just 0. So this ends up being then just pi times radical 3, which is going to give us answer choice C. For this free response problem, I have two regions, S and R, and two functions bounding them, the tan function and the 2 minus x cubed function. And among other things, they want me to figure out the area of R. So to make my life easier on this problem, I'm going to start by labeling or renaming these functions. I'm going to call this 2 minus x cubed f of x, so I don't have to keep writing it. And I'll also put that on the graph just so I'm really sure about what f is. And then for tan of x, I'll call that g of x, and I'll put that on the graph as well. Now, in order to find the area of R, if I'm thinking about this in terms of top minus bottom functions, there's actually two top functions across this region here. The g function is the top function for a while, and then it hands it off to the f function. So I'm actually going to need two integrals if I integrate this with respect to the x-axis. And I'm going to need to know the intersection point of f and g, and also where this f function is hitting the x-axis, because they didn't tell me that. So let me start by doing f of x equals g of x. I'm just stating that I'm about to find this. And I'm going to do this on the calculator now. So here I am in my y equals. I'm putting f in y1, and g is going to be the y2 function here. And let me just do, this is actually pretty close to the origin, I bet. So let me just do zoom 4 and see if I can get a basic picture of what's going on. So we've got a few extra things going on because of tangent that they don't show in the picture they gave us, but this is really the only intersection we're concerned with here. So let me do second trace, option 5 for intersect, and let me get my spider closer to that intersection, press enter 1, 2, 3 times, and that intersection is about 0.9022 for the x value if we round off. Let me quit out of there, and I'm going to immediately store that as a constant on the calculator. I'm going to do the constant p, but you can pick whatever letter you want. And I'm also going to write on my paper what I just did. So these intersect at x equals p, which is approximately 0.9022. And now I can just write p instead of writing this number over and over again, because I have a feeling I'm going to be using this multiple times on this free response problem. Now the next thing I need to know is where the f function is hitting the x-axis. So let me set f of x equal to 0 and solve that on the calculator. So let me go back to my calculator. Actually, let me do second trace, and I can just do 0 for this one. And now let me click a little bit to the left, a little bit to the right, one more time, and that intersection is at about 1.2600 if we round that off. All right, or 1.2599. Let me quit out of there, and I'm going to store that value as q, just so I can access it quickly. And I'm also going to write down that I did that. So q is that intersection point for the x. All right, so next, to find the area, I need two integrals. I need the integral from 0 to the p value, the x value right here. And this is going to be the g function minus 0, so just the g function really. So g of x dx. Plus, I need to add the integral from p to q of f of x. So my top function is switching off. And I'm going to do all this on the calculator now. So here's what this looks like on the calculator. I've got the integral from 0 to p, where I stored my value here, of y2, that's the g function, plus integral from p to q of y1, which was my f function. And pressing enter on all this, it's about 0.729. So there's my area. To find the area of S, which I have to do on this part of the problem, I can think of this in terms of top function minus bottom function and integrate that. So this is going to be the integral from 0 to p, where I stored this intersection point in my calculator. And I also labeled it on paper so that people know what I'm talking about. So from 0 to p, we're going to be doing, this is f of x up here, this is g of x down here. So f of x minus g of x dx. Calculator time. So here's what it looks like on the calculator. I stored f as y1 and g as y2, these two functions here. So pressing enter now, we end up with an area of 1.161. For this problem, they want us to find the volume of the solid generated when S is revolved around the x-axis. Since this S region here has a gap between the area and the actual axis of revolution, we have this gap here that R is making up. We're going to do this using washers. So my area formula for my cross sections is going to be for a donut, essentially, a washer. I'm going to have pi times big R squared minus little r squared as the basic setup. And I have to now express these r values in terms of x. So my big radius, the outer circle when this is revolved, is going to be this top function here. This is going to be the f function. So I've got pi times f of x, the function squared, minus my little radius, that's going to be this inner function here that's forming the lower part of my area. So that's going to be minus g of x squared. And now I'm going to take the integral from 0 to p, because that's the S region here, and I'm going to be integrating just the a of x function I just wrote, so a of x dx. No need to write anything else other than the answer, which we're going to find on the calculator. To make my life a little less hectic, I'm actually going to put in y3 this area formula that I just created. So I've got pi times, this is f of x squared minus g of x squared. And then let me get out of there, and I'm going to do the integral. So math 9 from, we said 0 to p, so alpha p. And then I'm just going to do alpha trace y3, where I just stored that area function, dx. And that's going to come out to 8.332. On this no calculator free response, they're telling us R is a region bounded by the x-axis, the square root of x, and the line x equals 4. So although this is a no calculator question, you could pretty quickly graph these out. Here's a rough sketch of what all this looks like. So here's this R region. So for the first part of this problem, they want us to find the area of the region R. Since the only functions involved are the square root function and kind of unofficially the line y equals 0, we just need to take an integral from 0 to 4 of top minus bottom, which is just going to be the square root of x. And I'll write that as x to the 1/2. No calculator, so we have to integrate this by hand. So antiderivative, this bumps up to a 3/2 for the exponent, multiplying by the reciprocal of that, 2/3 x to the 3/2, evaluated from 0 to 4. So plugging in 4 and 0, this is going to be 2/3 times, let's see, this is the square root of 4 cubed, minus 2/3 times the square root of 0 cubed. And we probably could have just factored out this 2/3, but whatever, we're here now. This second term is gone, and we could actually just leave it like this because it's all constants. But if you want to simplify it, this is 2 cubed, which is 8, times this 2 in the numerator gives me 16 over 3. For this problem, they're telling us they want us to find the value of h such that the vertical line, x equals h, which is presumably somewhere in here, divides our region into two regions of equal area. All right, so the way I'm going to set this up, I know from the last part of this problem that the total area here was 16/3. So there's some h that when I take the integral from 0 to h of this function, it's going to give me half of 16/3, which is 8/3. So I'm just going to use this already anti-differentiated evaluation box from part A. I'm going to say that this 2/3 times square root of x cubed from 0 to h has to equal 8/3. And now I'm just going to solve this for h. So plugging in h and 0, we've got 2/3 square root of h cubed. And I'm going to do all this now inside a parentheses here so I don't have to mess around with this 2/3. And now I'm going to subtract 0 square root to the third power. And that still equals 8/3. And at this point, I can get rid of this 0. I can write this if I want as h to the, this will be, let's see, 3/2. On the outside here, I could call this 2/3. I could say 2/3 h to the 3/2 equals 8/3, but I don't like those denominators. I'm just going to multiply everything by 3. So now I just have 2 h to the 3/2 equals just 8. I just multiplied both sides of this equation by 3. Now to solve, I just divide by 2, and I'm going to raise both sides to the 2/3 power, the reciprocal power. So I have h equals 4 to the 2/3. This is the cube root of 4 squared, but I mean it's a constant, so I don't really need to bother going any further than this. I'm done with this problem part. For this problem, I want to find the volume of the solid generated when r is revolved around the x-axis. Since this whole area, region here, is flush against the axis, there's no spaces in between my area and my axis of revolution, I can use disks on this one. So my cross-section area is just going to be pi r squared. And the radius is just the distance between my axis and my function here. So that's just going to be the square root of x that I'm squaring and multiplying by pi. This is going to be pi times just x. And now I'm just going to take the integral from 0 to 4 of pi x dx. I have to do this by hand, though. So this is going to be pi over 2 times x squared, evaluated from 0 to 4. And I'm going to just take this pi over 2 outside the evaluation box. So this is pi over 2, and in parentheses, I've got 4 squared minus 0 squared. So this is really just pi over 2 times 16, which is going to be 8 pi. For this last part, they're telling us we have a vertical line x equals k that divides r into two regions, such that when we revolve them around the x-axis, we get two solids of equal volume. Find the value of k. So this one works a lot like part B, where you had to find an h that gave you half the area. So looking back on the last part here, the volume of all of this stuff revolved around the x-axis was 8 pi. So I need to find a k value that when I take the integral from 0 to k, I get a volume of half of that, a volume of 4 pi. So I'm going to just start with what I already got when I took the antiderivative here, this pi over 2 x squared stuff. And that is now going to be going from 0 to k. And now I want this stuff to equal 4 pi, half of the 8 pi that I got for the whole thing. So just plugging 0 and k into this, I've got pi over 2 times k squared minus 0 squared equals 4 pi. And at this point, I'm just going to divide both sides by pi. So I've got 1/2 k squared equals just 4. If I multiply by 2, I've got 8. Square root both sides, I get the square root of 8. And since we're over here in the first quadrant, I don't have to worry about k being negative. So just positive root 8 is what we're going with.